Okay, let's talk about torque a bit. It is twisting force, so like force is going to give us linear acceleration, torque is going to give us rotational acceleration, going to cause it. The definition is the cross product of force and distance, and the distance that force is applied. So you also oftentimes see it written as FD sine theta, but that can be misleading. So there's some terminology to help you set up all the problems. The first is line of action, where all you have to do is extend the force vector. And then the other thing is the moment arm, and that is the perpendicular distance to the axis of rotation and the force. So if we have this door here, and I'm pushing on it like this at some kind of an angle, to get the line of action, I just drew some dashes to extend the line. And then the moment arm is going to be the perpendicular distance, so eyeballing it's something like that. But this is a right angle. So, okay. So then if you were asked to find the torque applied by this force, you would take the force and multiply it to the moment arm, the length of the moment arm. So, rather than using this length, you are using this length. We can draw the individual components of the force, and the one we care about is the one that is perpendicular to the moment arm. So with whichever method you use, either you're going to make the force smaller and the moment arm longer, or the other way around. So just make sure you only use one method at a time. Okay, and then I just want to give a real life example. I don't know if any of you are interested in exercise physiology, but here is a drawing of a foot, and this is me trying to draw all the foot bones. And then this red thing is your Achilles tendon. So when you're running and you go to take off, that's when you want the most force. That's when you want, to speed up, get going real quick. So if we were to draw our moment arm, we have our line of action. We're like pressing down on the ground. So this is our, like a line of action. Okay, here I'm grumbling about keeping the pivot point consistent between each foot. So that's the little brown X that I draw on the end of the foot bone. And then, so the green line is the line of action, and then I'm going to draw a moment arm perpendicular from the pivot point to the line of action. Looking at the zoomed up picture, you can see that the moment arm on the right is greater than the moment arm on the left. So your body is able to apply the same force, it's just that longer moment arm is going to leverage it more. And you will get the greatest bang for your buck. I don't like that. You will get the most efficient use of your energy. So yeah, that's my plug for biophysics. Okay, now we can get into static equilibrium. Static equilibrium just means that our system is not accelerating rotationally or linearly, so you can set up every problem with your net force equation and your net torque equation saying that acceleration is 0, so the sum of the forces is 0. Alright, now that we've established that this system is not accelerating, we will draw all of the forces. Make sure you draw the force vectors from the center of mass of each object. So the beam's center of mass is going to be at 1.5 meters, assuming it has a uniform density. Alright, now we're going to choose where our pivot point is, and we are going to choose it strategically to help us get rid of an unknown. So we don't know either of the forces for the supports, so we're going to put the pivot point on one of them, and you can put the pivot point anywhere. All that matters is that you keep it consistent when you determine the distances for all of the other forces. Your choice of pivot point informs what sign the torque will have. So imagine if that force were super huge, which way would your system start rotating? So remember that counterclockwise is positive and clockwise is negative. Next, you can find F1 by moving the pivot point off of it. Next question. Okay, the question is asking if this construction worker should be worried about the cable breaking because he is sitting pretty far from the axis of rotation, the pivot point. So he is exerting a lot of torque, possibly, on this beam. So the cable is rated at 15,000 newtons, so that means that it's able to withstand that much force. So let's find the tension in the cable in this situation. Okay, free body diagram.
We have tension, and we have the mass of the sky, the force of his gravity. We have the mass of the sky, and we also have the mass of the beam. Okay.
Alright, so here I've extended this force, and this is the perpendicular distance to the pivot point. And the perpendicular distance for these is just along the beam because they're already perpendicular. Okay, and then if we were to do this, it's equal to 0. We're going to have the tension force and this distance. So we can find that they give us the length of the beam, so that's 6 meters. So it's going to be 6 times sine 6 sine theta, because it's opposite the angle they give us, and that's positive. And then we have the mass of the beam, force exerted by the beam, the distance to its center of mass, which is 3 meters because it's a 6 meter beam, and the human, and he is 2 meters from the end, so he is 4 meters from the pivot point. Okay, so that's one way to set it. Alright, so you draw the components of the vector. And this is going to be 1 here and here, 4 here and here. Same thing, but they give us this angle, so I'm going to use this one and say that it's t sine theta. And then you're able to just use the distance to here, which is 6 meters. And then we're going to subtract the others, and then everything else is the same. Notice it's the same even though we got it in a whole different way. It won't always be the same. Sometimes there are easier ways to get. As you can see, I'm not sure what the best way to show these problems is, so please let me know. This is the problem with the ladder held up by the cable. Drawing all of the force vectors, making sure to draw from the center of mass of the beam. Actually, this is a ladder held up by a cable. So I extended the line of action for the force of gravity of the beam, and I'm finding the moment arm, which is the adjacent side of that 60-degree angle triangle. And I'm using 1.5 meters as the hypotenuse because that is where the center of mass is for the ladder. And I'm giving it a negative sign because if that force were really big, the ladder would be rotating clockwise. So then I extended the line of action for the tension all the way perpendicular enough, and then the moment arm would be that adjacent side of the triangle. So the hypotenuse is 3 meters, so it's 3 sine 60. And that's all equal to 0 because it is in equilibrium. And then you can easily solve for the tension in the cable. Redrew the diagram to demonstrate the second method. So instead of adjusting the length of the moment arm, you adjust the force and take the component that is perpendicular to the moment arm. So that angle is also equal to 60 degrees, so it's mg cosine 60, it's still negative, and we use 1.5 meters, the distance to the center of mass of the ladder. And then our tension. Right now I'm going to draw the components of the tension, drawing them in every way you can possibly draw them. Yeah, so alternate interior angle theorem, throwback. So then that is going to be t sine 60 times the length of the meter, or the length of the ladder, 3 meters. Alright.
This has.
Okay.
Alright, this problem
So
is
we're
from
given this
the lecture
angle.
problems for today. I'm drawing in all of the forces. It's just a beam, an angle with a mass hanging off of it, and the cable is at a certain particular place, 5 meters from the pivot point. So I drew the force of gravity for the beam at around 4 meters because it has to be from the center of mass, and the tension in the cable is already perpendicular to the moment arm, so we can just do, say, 5 meters times the tension, force times distance. And then I basically have already extended my line of action. That's the moment arm that I just drew. And so if that angle would be 60 degrees, so then you know that this angle is 30 degrees. So I'm going to take the adjacent side, which will be 5 cosine 30. And then for the hanging mass, basically I already extended the line of action, so it's just a larger triangle. Same thing, and the beam is 8 meters long, so it's going to be mg, 8 cosine 30 times mg. Good job, Morgan. Oh yeah, label those masses. Okay, that's it for the static equilibrium problems. Hopefully you are feeling more comfortable with the two methods of finding the torques, and good luck on your quiz.